Right. Don't forget, you're going to want to start working on the student-led project. Do you guys want to do that as a team? Okay. Okay. Um, could you send me an email to remind me I need to make sure you guys can create groups so you can do it as a team properly? I appreciate that. All right. So, yeah, I'm not going to get to actually do anything for a while today. All right. Now, whenever you're looking at absorbances, keep in mind that so before we were looking at very separated peaks and things weren't mixing together, and so we don't have these issues before, okay? But when you have an actual mixture of things, whether that is peaks that are near coincidence to each other, or you have a mixture, literally a mixture, like of different substances, you can oftentimes get where peaks will line up either on the exact same frequency or very close together. Okay. And so one of the things you want to keep in mind is each of those absorbances will stack. Okay. They are additive. So the total absorbance at that place is going to be the two added together. Okay. So for example, can you guys read this okay? We have two peaks here, right? One here, one here. Y is here, X is here. So if the peaks that you see, so what you see as the spectra, is going to be the X plus the Y at each of these points. So if you just add those together, okay? Now, if we substitute Beer's law in here, then what we remember is absorbance is directly proportional to the concentration, right? Typically, the epsilons are going to be consistent for each of those substances, right? And so you're going to have epsilon concentration, which is what the absorbance is actually coming from, right? The path length will be consistent for both usually, okay? Because you're going to use the same vessel, right? All right. And you can even see this even better right here. See that? Where we have this stacking of this plus this gives us that. Okay. Okay. Now, this is actually something like if you were to go back like 50 years ago when computers were rare, this was very difficult to actually use. It is very difficult to use anything where peaks stacked on top of each other. Okay. Even 20 years ago, this would have been fairly difficult to do. Nowadays, it is much, much easier, but it's still not 100% reliable. Okay. Because keep in mind, you do have two things that are changing as you change your wavelengths or you change your frequencies, right? What are those two things, by the way? It's what I had said just a little while ago. So the two things are changing as you go along here is epsilon, right? Your absorptivity. Okay. The other thing that's changing is you don't necessarily know your concentration. Okay. And so like you're oftentimes trying to do this so you can figure out your concentration. It's not something you typically walk in with. Okay. And so epsilons are changing as you go. The concentrations are not changing as you change your wavelength, but you don't know them. They're a variable that you have to solve. Okay. Okay, so when we're talking about multivariate calibration, this can be models that use more than one measured variable to make quantitative predictions of analyte concentrations of the sample properties. For mixture compounds, we can actually distinguish two cases. One is where we have relatively little overlap of absorbance. And so one of those is going to be the primary cause of our total spectra absorbance. This would be a case of that right here, right? We have very little absorbance from one species. We have a lot of absorbance from the other. This is not a perfect case, but it's a decent case, okay? You can get better cases, of course, where you'd have one like right here, right? Now, for those, the absorbance here is going to be pretty close within the an error limit, right? Of just directly Beer's law, now I know my concentration. Okay. If you change this, you can actually tell, you can build up a Beer's law diagram, graph, and then actually fit this, right? Okay. And so the other one is going to be where you have significant overlaps. So for example, here we have significant overlaps on all these. This is another one where we have significant overlap, right? And so both species play a significant part in that total absorbance, don't they? And so these ones right here, if we want to find the composition of that type of solution, it's going to be best done with a spreadsheet, actually, because they're both going to play large parts in this. The increased accuracy results from having more measurements than unknowns. If you have the same number of measurements as unknowns, you can get some data. If you have less measurements than unknowns, you really don't get anything reliable at all, to be honest. It is a very, very bad idea to try to do that. So the more measurements you have than unknowns, the better your accuracy is going to be. So in either of these cases, the first measure the absorbance of each pure compound as standard at several wavelengths. You'll determine the molar absorption coefficient of each component at each wavelength from your Beer's law. So if you put in everything else at that specific wavelength, you can actually figure out the absorptivity, can't you? The epsilon. Can everybody see that's just rearrange Beer's law? No. So the AXS, this is the absorbance of our standard. The X here, the concentration of our standard, right? Okay. Now, if we go ahead and put this in, then the more measured absorbance of an unknown mixture here at each wavelength is going to be the sum of those components. If you have the epsilon, you have the path length, well, then we can actually predict those concentrations much more accurately, can't we? Okay? Mm-hmm. Yep, and they always combine them linearly. So the absorbance is always going to just be these added, aren't they? Okay. Is that starting to make some sense? I know, like, when you look at the end result, it's super complicated looking, right? But in theory, in your mind, it's not that complicated in theory, right? You just got to solve the parts of this. Yeah. So these are some of the requirements for this analysis of our mixtures. The spectra of the components must be different. If we have complete overlap, it's really just not going to help us out. We don't have any places to actually look for the individuals, and they're going to be very difficult to resolve anything. The number of wavelengths must be at least equal to the number of absorbing components. More wavelengths are definitely better, but at least equal. If you have less wavelengths you're trying to do this at than you have number of components you're trying to resolve, you really won't get anything reliable at all. You'll actually won't be able to solve it to a single answer. It'd be like having not enough variables. You know how you need like the same number of equations solved for variables? So you always want to try to get the wavelengths that are separated for one as best as you can. Okay? The more of these you have, the easier this is going to be to actually get solved, and the more reliable your data is going to be. So, for example, we would definitely want to include this one, right? That one is our best peak right there. That is going to give us our best data. So in this case right here, we actually have two peaks that are pretty decent. We have this one, which is very good, actually, about our optimal case, actually, in this spectra. And then the 447 is actually reasonably useful. See that? Because this is only over here, isn't it? That really contributes a lot. Over here, we're 447. Well, this one's actually almost all that, isn't it? Yeah. So it's almost all one species there. Remember, it's just linear across this entire thing, isn't it? Now, you can't really see this that well because it's very low resolution looking. But if you have higher resolutions, you'd be able to see these peaks break up a little bit right here. You'd actually see a little like divot. Okay? Because it falls off more right there, right? So you'd look up or experimentally measure the molar absorptivity coefficients for these wavelengths, the 447 and 612. And then you'd plug in your known variables, and then you'd solve the two equations simultaneously to find the x and the y. Okay? Again, this is actually done easiest through programs and spreadsheets. I don't think I've seen anybody actually do this manually with like a calculator, except for in classes, in like ever in my career. I honestly can't think of any scientist that actually has done this manually ever in my career. Because there's programs that will actually do this for you. Okay. And so unfortunately, we get really lazy and we kind of start forgetting things on this, which is actually terrible if you think about it. But I want you to understand how to do it on simple cases. Spreadsheet is going to be your friend on doing more complex cases, like you might see in like homework or something like that. And then you can go on to do this with programs usually. Usually they have a program in your spectroscopy package that will help you do this. Okay. And it'll actually graphically fit these. Because remember, these are actually numbers on like essentially what would be a table. Yeah. And it's just plotting those as a graph, essentially. Okay, so this symbol right here, this is called a determinant right here. And it's just a short way of writing the product. And so what the product would be is, have you guys ever seen these before, the determinants? Okay. I figured you had because you guys have pretty advanced math. For like this course, I don't think necessarily has, I'd actually have to look. I need to find out what the calculus teaches here, what the different levels calculus teach. Oh, cool. Okay, that's awesome. Yeah, so the determinant here is we're just going down across. And so this times that minus this times that. And that's all that is. So whenever you see this determinant, that's all it's going to be. Okay, and so our previous problem we were looking at, this is actually how you would write that out. Again, we'd have our absorbances right. And so we have our two equation sets for two variables we're solving for. And so we can go ahead and write it out in terms of determinants, or we could write it out in terms of the formulas, right? And they actually mean the same thing. So this is just the same thing twice. We have just solved this so that x is on one side for here, y is on one side for that. And we just substituted one to the other, essentially. Or we've taken this divided by that, right? Okay. Does anybody have any questions there? Everybody understands prime here, double prime. This is one way you can denote like which is which for the equations, prime first, double prime second. I guess you guys probably have seen that. So. Okay, so let's try an example real quick, and you guys can get out your calculator. This would be about as complex as you would normally see for doing these manually by hand. Because after 3, it starts getting long. And it becomes much, much, much easier to do it in spreadsheets. Okay. Or technically, it would actually be pretty easy to do with like R or Python. Most people, however, don't actually program the programs that do this in Python and R. They program it into a little bit more efficient languages. Fortran versions are pretty popular to these calculations on low capacity computers. But there's other ones, of course. Actually, should look up what Omnic uses for its language to program that. Wonder what they do. I'm not actually going to hit on the spreadsheet stuff that much in class because there's not a lot I can actually like help you out entering data in spreadsheets. But I'm going to put it on that slide and ask you guys if you don't understand it, okay? Because there is oftentimes places where you guys are like, I'm not sure what that's saying. Please do actually go through and do the spreadsheet though, and go, Dr. Clausen, I don't understand what the hell's going on. Come and talk to me, okay? You'd be surprised how often I've had to make these spreadsheets in my career where I'm just not getting what I want from the programs. And they're having a weird error, and I have to figure out what the hell's going on. Okay, you guys good? All right, and so, is that what you got? Yep, both you got that? No problem? Okay, fantastic. Do always make sure that you actually try it and double check, because even relatively basic things can end up having a part that you just don't remember how to do and mess you up. Okay, so you can, of course, do this with Excel. You can do the simultaneous linear equation solving with Excel. And so this would be the table you put in. This is what's in each of the cells here. Okay? Is there anything you guys don't understand about that? This does not work well in Sheets, by the way. So you really do want to get Excel to try this out, okay? Anything you're struggling with there? Okay. So whenever you look through, like, what's in B5 here? Yeah, so this is going to be those coefficient matrix, the EB. That would be the E epsilon times the B path length. Okay. That you put in there. Okay. Mm-hmm. Yep. Same as this. So these are just these values here. Okay. Is that making sense? Okay. Okay. All right. Try it out. Let me know if you have any issues. Okay. It really does kind of make it easier to do in Excel spreadsheets, to be honest. Okay, so this is actually going to be using more wavelengths than unknown. Again, once you get to 3 and beyond, the math starts getting so long that really it's just worth putting in a spreadsheet. So you're going to have to take a slightly different mathematical approach since there's not going to be more equations than you have unknowns. So if you have a highly overlapped mixture spectra, which you're going to have to use a classical ordinary least squares analysis of that mixture. The spectrum is going to be used to find the concentration of each component in that mixture then. And so right here we have a mixture of p-xylene, toluene, and dichloroethane that we're seeing here. The dichloroethane is the solid green. The mixture one is the dotted green. Okay. And you see it's fairly complex combinations, isn't it? Everybody see it okay? Okay. But we have lots of bands to take, don't we? See, we have all these bands to take. Yeah, some of them are actually pretty decent bands, right? And so we can take those bands. We're going to enter them in at several different wave numbers. And that's going to be our column A here, the wave numbers of our bands. And then we're going to record the absorbance or mixture. And again, that's going to be column E here. Okay. And then we're going to record the absorbance of our standards and put those into these columns here for the different substances at those different wavelengths. Okay? And so we would run a p-xylene, we would run a dichloroethane, we'd run toluene, all individually. Is that making sense so far? Okay. Make sure that you do know the concentrations of those. Okay. And that's that data right there. Okay. And so then what you're going to do is you're going to put these equations that are right there, see those? Notice those are the same equations you saw in that previous case, so at the determinants. And you're going to use the solver to solve for those. Okay. Right. Anybody have any questions there? Okay, so let's actually set up a model. Let's try kind of doing the reverse, where we would predict what the spectra would look like if we have each. Again, this is where we have the model is going to give us this absorbance calculated for that mixture. Okay. So again, that mixture one, the absorbance, is just going to be the absorbance of each of those, right? Each of the components of the mixture. And so we need to calculate the molar absorptivity coefficients of each component from Beer's law from our standards, okay, for each of those components. And then what we're going to do is we're going to make an initial guess of our concentrations. And so that actually would be the I-15 to I-17. Again, it's arbitrary. It's an initial guess. You can just do one if you want. It's will take less time and give you more consistent results if you get something that's close and reasonable. But, it's initial guess. Don't get so stuck in the trying to guess it that you don't get anything done. Okay. Now, the calculated absorbance of your mixture will then be computed in your column I. And this is going to be this absorbance calculated. And again, it's going to be the epsilon times the B path length, which should be consistent for each of those. And then it's going to be your guess value for concentrations. So it would calculate that, and then, probably too high or something. And then it's going to shrink each variable down to fit each. So finally, the calculated fits. Now, what you're going to do is you're going to give column J, so right here, this is the difference, the square of the difference between the calculated and measured absorbances. Okay? One of the reasons you always want to use squares is that's going to get rid of your positive and negatives. Also, this least squares fit. Okay, reduce the squares difference. Okay, so that's again absorbance calculated minus the mixture squared. Okay, don't forget the parentheses because then you get very different value. All right. So your least squares condition is going to be to minimize the squares of your values. And so if you sum those, you're going to want to decrease that sum to the lowest value you can get. That's going to be your condition you're going to try to do. And this is going to be by varying the concentrations that you guessed of X, Y, and Z. Okay. So your best values of X, Y, and Z, those are going to be in I-15 to I-17, which is down here, which is the green stuff. Okay. And these are going to minimize your sum of your squares in this. So those are the two things you're going to put into the solver as what am I minimizing and what do I use to minimize those. Okay? Is that making sense so far? Or did I completely lose you? Yeah, without actually making the spreadsheet, it's a low. Yeah, please try to make it. And I do recommend before you actually try to do like a homework problem where you don't know what the result should look like, you actually make the sheet. Okay? Because you know what the result should be here. If you don't get that result, then you know something went wrong. Okay, this is going to be the inverse multivariate calibration. So for complex samples like gasoline, food, it's very unlikely that all the components are actually known. And so doing known spectra of each of those is just not possible. You really just can't do it. So if you do a least squares analysis with molar absorption coefficient for some but not all of the components, it's actually going to give you these really wildly inaccurately predicted concentrations because you just don't know what the contribution from those things you don't know yet are. So the inverse multivariate calibration methods is going to be used for your spectra for some of the components of a mixture that are unknown. They're going to be analogous to rearranging the form of the Beer's law for one component. And so again, this is Beer's law. If we rearrange this, we can put concentration on one side like we did before. This is just another rearrangement of that where we put P as a variable that represents this 1 over epsilon B. Okay, it's just the regression variable. Okay, so we have our regression variable that we've listed here. So if we have a mixture of components, some of which we may be unidentified, we can attempt to find relations in matrix form using the absorbance at multiple wavelengths. So for the analyte X, we assume the expression would be something like this. So we have our analyte here. We have our regression, which is 1 over epsilon B, right? And this is going to be times the absorbance. Notice that's just Beer's law, right? Okay. And this is then going to be plus, well, the next wavelengths, 1, and then plus the next wavelengths, 1. These all have to come from the same concentration, don't they? So we know the concentration has to be a set variable that's the same for all of them. I always find it funny that they put the path length in these, which fair enough. I guess they wanted the option that the path length could change. I always find that kind of amusing, actually, because the path length on most instruments would have stayed the same too. So you could have just taken that one out. But whatever. Doesn't really matter that much. Usually 1 centimeter anyways, right? So your matrix that's actually going to be formed from this is going to be your concentration. Then you have P, which is your regression vector. And then you have absorbance vector right here, which is your absorbances. Okay. Does that look familiar? Okay. Yeah, you're just going to go through. This is just another way of representing this. Okay. So this one multiplied here, this one multiplied here, and so on. Is that making sense? Did you take linear algebra? No. Okay. Okay. Does this make sense that this is just a rearrangement of this? Yeah, I'm gonna have to develop a module that basically is like a training in vectors. Because yeah, it's that'd be better. Okay, so your inverse multivariate calibration is going to estimate the regression vector, which is this P here. We're going to do that by measuring the absorbance spectra of many calibration samples where your analyte concentration or other properties have been determined using a reference method. So for multiple calibration samples in spectra, we actually would expand this standards one right here, which is the absorbance matrix right here. And then what we would end up getting is from this, we would get a set of concentrations that have been predicted by these. Okay. And that would be this, however many we do of these, we're going to get the same number of these. Okay. Now, hopefully they're repeatable. Ideally, they can all be basically the same number here, right? But as you've seen from real life experimentation, right? Rarely does ideally come into play. Okay. So you're probably going to get a range of these. Hopefully, they're fairly close together. Okay. So if we solve for P here, we're going to repeat to find regression vectors for all other known compounds. And we can just do this for all of the unknowns. Essentially, what we're going to do is we're going to take our samples that we have, we're going to divide them into a whole bunch of samples, okay? And then we're going to run those samples under various conditions where we think that we can isolate that sample, what we're looking for. Okay? Is that making sense? And by taking all of those and running them through this inverse multivariate calibration, we're going to get a range of concentrations You can eliminate ones that are very far off using, of course, the G-test from way back in the semester. And that will hopefully give you a pretty good regression vector that's reliable. Okay? Okay. So again, this is that same formula we were talking about before. So A does not necessarily have the same number of rows as columns here. So we're going to use this as a pseudo inverse A plus instead of its inverse, which is A minus. And so we don't necessarily have to have the same number of rows and columns because we may not test the same number of wavelengths. See, those are those. There, right? Versus the number of different samplings. Okay? Okay. So what we're going to end up doing here is this mathematically is going to be represented by, okay, I'm going to try to give you what I can of this, but this is the linear algebra here in the university, right? They don't cover this in the calculus. Okay. 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 Yeah, it's transpose. Yeah. Which, interestingly enough, is the exact same operation as inorganic chemistry. Yeah. Flip, right? Flip, rotate. So you do end up transposing the sort of questions I'm going to ask about this. I'm going to stay definitional on this, okay? And not dive into the mathematics here, right? Because that's a bit much for what the stated mathematical level of this course is. Okay. So if you do this, by the way, normally actually you do this in a program, and so it does the matrix math for you. And so realistically speaking, unless something goes wrong, you actually won't actually have to like do the math and try to figure out where it went wrong. All right, so the analyte concentrations or properties of interest of an unknown sample are going to be determined by using this right here, which is the concentration of unknown, the regression, and then the unknown absorbance right there. Okay, so your calibration matrix, this can be constructed by a number of inverse least squares methods, actually. So you can stack together multiple linear regressions to construct this. If you use multiple linear regressions, the wavelengths are going to be chosen manually. They're going to reflect your absorption bands of the components of interest. This is most useful where you find that when you start isolating different components, they have significantly different bands that they show up than other components of that mixture. Okay? Now, these are going to be chosen manually. They're going to reflect the absorption bands of the components of interest. These are must be at least as many calibration standards as wavelengths that are used. Unreliable calibration is going to result if the calibration standards are not sufficiently different. More robust factor-based methods are going to be things like principal component regression and partial least squares. And these were actually created to replace the original variables with small numbers of variables derived through linear algebra from the original variables. And so when you do these fits, what you're going to see is if you ever have to do one of these fits, okay, you're going to go into a program that's on your spectrometer, okay? And sometimes you have to buy it as an addition, depends on the manufacturer. And what's going to happen, there's actually people that make these, by the way, they just make packages that do this. And then they read spectra from different corporations. And so what's then going to happen is you can select the methodology, okay? And the methodology will give you slightly different results. And so what I'm trying to give you here is I'm trying to give you a little bit of the math and a little bit of how you do this. So if things go wrong, you can understand where it went wrong. But also, so you have an idea of what you're using and what will work best as your selection. Okay? So this right here is actually a near-infrared spectra with multivariate calibration analysis for key components of like modern farming. And so what you have here is you have your spectra right here. And these are different components that we've identified here. And they're different nanometers. And then this is the deconvolution of the absorption into 3 different bands here. So you see how we have these 3 different bands, 1, 2, 3. They're accounting for this overall shape right here. Okay. And that deconvolution is just separating out the different components that construct that. Now, this is a very experimental approach when you do this. If you put things in and it doesn't fit what's up here, then you have a negative result, right? And you need to change your hypothesis. Instead of there being 3 bands, there might be 2 bands, there might be 4 bands, etc. Okay? Okay, by the way, this right here, why you would have predicted that there might be 3 bands, is you'd put the first 2 in, which are there and there, right? Do you see that okay? They would have been there and there. And then you would see that this should have dropped out right here. There's actually one more that you can kind of see like right there. See that? Where it has this like, it should be dropping, and then all of a sudden just instead. Right there. Do you see that feature? Mm-hmm. Yeah. Yeah, the deconvolution is probably right. These 2 are the obvious peaks. That you can see actually like where it's the top and then it comes back down. This one's more difficult to see, but what you see is right there. Yeah, the bottom you can see it easily because they've deconvoluted, but this right here should be dropping here, right? The fact that it's off here means you have a much smaller peak right there. And that's how you'd start your predictions. Okay. So the absorptions features of wheat and near-infrared spectra actually rise from weak overtones or combinations of fundamental bands like carbon hydrogens, carbon nitrogen hydrogens, and OH vibrations. Do you guys remember overtones and combinations? Okay, so overtones are going to be 2 times your band, so you get double excitation. And that's going to give you a twice the wave number. Okay? Or twice the energy it takes to do that. If you have a combination, it's going to be 2 bands. So this might be a CH and an NH, both happening at the same time. Okay? And it's going to give those 2 energies added together, minus a very tiny amount, because it's always a little off. Okay? But theoretically, it should be that number. So overtones are going to be excitations from ground to a second or third excited vibrational state. Most spectroscopy, you see the second is going to be pretty often. The third excited vibrational states are going to typically drop off in terms of your amount and intensities, but you can still see them. Okay. Combinations, simultaneous excitations of 2 vibrations. So that's going to be 2 vibrations that are both happening at the same time. We excite both. Kind of like you can go like this, right? It takes the combination of those 2 energies, right? Okay, so this right here is using this on the farm, of course, because we're looking at farm data. And so we're going to compare the protein concentration determined using near-infrared with multivariate calibration versus Cajal reference method. And so the black ones here are the validated multivariate calibrations. These ones right here are the data used to construct the multivariate calibration. And so those are the green without any filling. Okay, the black ones are the validated ones. That making sense so far? Okay. Anybody have any questions on this material so far? Okay, so let's talk about equilibrium constants then, and measuring those equilibrium constants. So this is one of the things this is used quite extensively for. Um, Interestingly enough, this is actually what part of my research was back in grad school. So I have like 20 something publications that have stuff like this in it. Very easy to do with xenon solution mixtures because you can change the temperature. Okay. And so you can take a chemical reaction, or you can take it's not just chemical reactions, really any equilibrium can be done with this. So you can take things like conformational interchanges. Those also can be done with this. So you're going to have one absorbing species, X, of course, one absorbing species, Y. The spectra of the pure X and Y are going to cross each other at any wavelength. Then every spectrum recorded during this chemical reaction is going to cross at that same point. And this is going to be called the isosbestic, excuse me. God, you can tell I don't drink enough water in my previous class. Sorry, guys. Isosbestic point, and that's this point right here. See how they all cross at that exact same point? Okay. This is actually really good evidence that you have two principal species that are linked in this equilibrium. If you see that, is a very strong indicator that there's going to be just two principal species and they are related through some equilibrium where one is rising as the other falls. Okay. And it doesn't really matter if they're like a 2-to-1 ratio or 3-to-1 whatever ratio. They'll still have this isosbestic point. Okay. So this right here is going to be the bromomethyl blue converting to its conjugate. That's the same sort of conversion that you would see for doing like a titration or something, right? And so the two absorbing species are going to have the same molar absorption coefficient at the isobestic wavelength right here. Excuse me. And so this is what this looks like in terms of your math. See, these are the two absorbances like we've been doing before, the two Beer's law, right? That we're splitting up. Because these values are going to be the same at that point, they can actually be taken out into the outer portion here, along with the path length, which is also not going to change as you go through this reaction. And so the isosbestic point is going to occur where you have two absorbing species that are involved in an equilibrium reaction. The two absorbing species are going to have the same molar absorption coefficients at that point, not the other points, by the way. The other points, they can't have the same molar absorption coefficient if they look like this, because they look different. The sum of the concentration of your two absorbing species is going to be constant. And so X plus Y concentration will equal a constant, because as one goes away, the other is going to increase, right? So if we suppose there are species P, like a protein, and a ligand X react to form PX, we can actually use a conditional equilibrium constant. We write this conditional equilibrium constant like so. The prime is conditional, by the way. That's what that's indicating. This is going to give us concentration over reactant, right? Everybody's comfortable with that so far? Okay, if we determine to determine that conditional equilibrium constant here, we can increment the protein as we add that to a fixed quantity of ligand, and the absorbance is going to be measured. You'll actually recognize this same concept from biochemistry, actually, because this is how a lot of those equilibrium constants can be determined. So, okay. So remember, we are incrementing the amount of protein here with a fixed quantity of that ligand. Is everybody okay with that so far? And then measuring that absorbance. All right, so this is actually doing that. So we've added protein to a fixed quantity of ligand, which is this X here, right? And so what you see is as we add protein, right, it consumes more and more of the X, and the X goes down. Okay? You see that okay? And so, again, this is going to be the On bound X is over here. That's the pure X curve right there. This right here is going to be the bound protein as we added more and more of it. Right. So the absorbance of any wavelength is going to be the sum of the absorbance from the X and the px. If we let the x0 be the total concentration of X, we can actually write this out like so. And so the X is going to be that x0 minus whatever amount got turned into the protein complex, right? And so we can substitute that in, and this makes this much, much easier to solve, and it makes it, linear. So we have the absorbance equals the epsilon right here of the X. This is going to then give you the x0, which is that original concentration before any protein is added, minus the px, which is the amount that's bound. This is going to be plus the epsilon for the absorption for the px, which is going to be the protein bound complex. So if the P0 is the total concentration of P, both P and Px, we can find the P with our mass balance. So now we need another calculation, right? We need another equation so that we can solve this system. And so we write out our mass balance equation. Everybody recognizing this from analytical? Yeah. Okay. All right, now we're going to substitute in all of our equations together so that we can get something we can solve. All right, so we have our equilibrium right there, don't we? And we're going to substitute in each of the terms that we've discovered so far. So we have px here. This is going to be p0, which is a constant, isn't it? Okay. Minus the px again. This is going to be the x0. That's that constant that we have of the concentration. We took the spectra. Minus the px. We can rearrange this in a form that's going to be in the quadratic equation form, so we can actually solve it. We'll get two answers, of course. One negative, one positive, right? From the plus and minus. And any solution with a negative sign in the numerator is the one we actually want. Because this is going to be going down. So the one with the negative sign here in the numerator is actually the one we want. Okay, so if we go ahead and put this in, we have the epsilon x, we have the epsilon px, and we have the equilibrium constant. Those are the only things that we have that are unknowns. The epsilon x at 545, we can determine that by just taking a pure X sample, that pure substrate that we're binding to that protein, and taking the spectra for that, right? If we know the concentration, we know the absorbance, we can get the epsilon, as long as we know those things. So we do not know the px. So the px is always going to be an unknown with a mixture of X, because it depends on the protein binding to that. So what we're going to do when we go ahead and calculate this is we're going to estimate our equilibrium, our conditional equilibrium, our epsilon px. We're going to calculate the resulting absorbance from Beer's law for the mixture, which is this equation here that we had discussed before. And then we can use Excel Solver to adjust the values of that K prime and epsilon px until the calculated absorbance at 540 nanometers as close as possible to the observed absorbance for all 10 additions of our P and X. So this is what that's going to look like. These green ones are the ones we're feeding in, and this gives us that sum right there for our average squares value. Okay. This is the graph, by the way, and this is the fit right there. So these are the observed values, and that's the fit. Anybody have any questions? Okay. So let's talk about spectrophotometric reactions. So spectrophotometric analysis, we can perform this by treating a sample with reagents that convert specific analyte into colored product. And we've already talked about this a little bit and indicated this in actually a bunch of the previous chapters, but this is more, we're taking that concept and we're trying to solidify it. So excess reagent is going to be used to ensure the conversion is rapid and complete. You don't want to have any of your concentration that ends up not reacting. Masking agents and pH control may be needed to ensure selectivity. Because remember, multiple species may do this reaction. You got to be very careful about that. Okay? And that's where those chelating agents came in that we talked about, and the different masking agents that we've talked about can come in. Also, pH control, so you have the correct species. For example, if you use specific pHs, you can subdivide out like lead, right? You can do the same thing for species of acid-base reactive. Let's say we had like several indicator dyes. Well, you can change some of them so they're different colors so they don't show up in your spectra as much, right? At that wavelength anymore. So these determinations are going to be rapid. They're actually pretty simple to perform once you've actually set up your operating procedures, because you can make them very simple where you just add this, add that, do the spectra, use the program fit, you're done. Okay? And so they can actually become a very fast, very easy to automate, in fact, and require very inexpensive equipment. A visible light spectrometer is very cheap. Once you get the development costs out of the way, the electrochemical probes can also be very cheap as well. So many of the samples can be analyzed at the same time. Many analytes can be measured by treating sample aliquots with different reagents. And so you can subdivide samples and then treat them with different reagents to select for different components of that sample. So let's say you're looking for PFAS out of that sample. You can specifically target PFAS in one test, and then dichloromethane in another test, etc. Okay? All right. So this right here is actually the spectrophotometric methods for analyzing water samples. These are different species that you're analyzing, and this is the reaction you're looking at and the wavelength you're monitoring. And that's your standard method here. So for example, like chromium, this reacts with diphenyl carbazide to form red-violet colored complex at 540 nanometers. So if you add this in excess, you're going to get a nice band of 540 nanometers. That's going to be directly proportional to your chromium amount in that water. Okay? Incredibly important, because did anybody see what the number here for chromium is? Oxidation number 6, right? So that's hexachromium. It's very toxic. Really bad for humans and all life. Okay. Does that make sense so far? Okay, so colorimetric kits. Again, you will actually recognize these pretty quickly as being something like heavily utilized in biochemistry again. Okay? Very, very popular biochemistry method. Now, colorimetric kits, these are going to support your photometric determination in industrial plants. In the field, at home, you can use them for analysis of aquarium or swimming pool water. Essentially what this is it's just a way to do this test that's more field portable. Okay? So it's the same sort of test we just looked at. You're going to have a simple volumetric glassware of some sort, usually some sort of syringe with a little vessel container that you put it in. Okay? Dropper bottle reagents, they can be satchels or pre-weighed powders. So field agents that you're sending out, you can train. You typically send with like bottles where they put so many drops in, and you depend on them doing that. When you're sending kits to people at their homes, you typically do not give them bottles. What you give them is like already pre-portioned amounts, and in the vessels, in little tiny vessels, and you have them put the stuff they're testing in. So this is going to be one of the things you're going to need is a means of quantifying the color intensity. You can use a colorimeter in which the operator compares the sample solution color with standard colors. You've probably seen this if you ever seen a pool. Have you guys ever had to do the pH thing for a pool or seen that done? Okay. If you ever seen that done, those kits that's this. Okay. Or if you've ever had your water tested by a field agent, very likely they did this. And so you have like a little color wheel that comes with it, and that tells you what the different deals are. If you go to like Walmart and get pH paper, you'll see that it's the pool kit and it's just like this. Okay. So let's talk about discrete analyzers. So this is actually going to be an automated system. It's an automated wet chemistry system where the spectrophotometric determinants for thousands of samples are going to be analyzed daily in environmental, food, and clinical labs. So discrete analyzers are going to have an automated analysis. You'll load in a round of samples. Some of these analyzers are actually quite interesting because they can have a feed that you literally just put containers and they feed and they automatically scan them. Or some of them actually have like little drums that you load. So you load the drum and then you drop that in. So they can be quite interesting, actually. They're going to do automated analysis so you can rapidly move through these products. You guys may remember this from Pace Analytics where they had like the trays they were setting in and did automated analysis of the stuff in the trays. So many reactions are going to be performed on the samples. The speed is going to depend on reaction time and number of reagents that are required. They have actually surprisingly low reagent consumption because they're doing micro amounts, just very tiny amounts, right? So you can get away with using pretty small amounts. Micro plates or multi-well plates. That's going to be a microplate or multi-well plates. You may have seen these before, especially like in pharmacy. Okay. Or maybe in biochemistry. I'm not sure. Yeah. They're going to have two-dimensional arrays of small volume wells. Each well is going to serve as an individual test tube, essentially. The microplates are very popular, of course, in microbiology because they have many samples they typically need to analyze, and the sample volume is very limited. They don't need a lot, and the reagents are very, very expensive in a lot of these operations, and surprisingly toxic. Micropipettes are oftentimes used to dispense solutions into the wells. The micropipette plate reader instrument will rapidly read the absorbance of each sample well. Now, there's actually a variety of different microplate readers that you can use. Do we have a microplate reader? I don't think we do we? I don't think we do. Essentially what they do is they look for the colors here. We do? Okay. Cool. You can actually do this with Raman and infrared as well. There's actually an attachment we can get for the spectrometer that does that. It's very expensive, but there is an attachment. So microplates again. So the microplates for the spectrophotometry is going to have a flat bottom well. This is one of the ways you can actually tell the difference between microplates that are used for spectrophotometry and the ones that are just used to do like reactions where you look at the top. The reaction ones where you look at the top are going to have round bottoms. So the bottom's going to be transparent. It's going to be made out of one of the materials that you would use for each of the different spectrometries. For example, if you're using visible, polystyrene and glass both work fine. And so typically polystyrene and glass. Polystyrene is actually really nice because when it starts scratching, you can just throw it away and get a new one. So they oftentimes do that. You can also make them out of quartz or cyclic olefin copolymers. That'll be for ultraviolet. Those are much more expensive. So, the nice thing about quartz is it's very hard. So it's actually not likely you're going to scratch it up as long as you're reasonably careful with it. So the luminance or fluorescence, the sides are actually going to be opaque so that the fluorescence and luminance doesn't scatter out into the different wells. So this is actually how you can tell the difference between a luminance and fluorescence one and one that's specifically not designed for that, which would just be a transmittance. In the cuvette, your path length B is going to be the width of your cuvette. So in plates, the irradiance is going to pass vertically through each well. Your path length does actually depend on your volume, see? That's your path length there. So if you fill this up with different amounts, your path length is going to vary, right? You do have to watch out for that. So your reproducibility of your delivery volumes is incredibly critical. And you both taken the biochemistry where she does that spotting, training you to use your micropipettes. That's why. Because there are a lot of tests like this in biochemistry and microbiology applications. And reproducibly delivering the exact same path length is absolutely key and important. Now, what did I say? Did I say you have to get the accurate path length, or did I say reproducible? And is there a difference? There's a difference, right? You don't actually need the accurate path length necessarily. Most of these tests, you just need reproducible path lengths. Okay? And so that actually is also calibration of your micropipettes matters in getting an accurate path length. Okay? Okay, so this is that optical path length through that micro well there. It's going to be an aqueous solution in a well. We can determine this using our equation here. So our path length for our well is going to be the absorbance of the well versus 1 centimeter cuvette. That blank correction for the absorbance of your solution in the 1 centimeter cuvette would actually be this right here. This is how you'd calibrate that. So then you could test these very accurately with a cuvette. So you get an extremely accurate measurement. And then you can convert that for use in these micro wells. Okay, so this is an example right here. DNA can be quantified as absorbance of 260 nanometers. The readings for the 230 microliter sample of DNA in 1 microwell of a 96 well microplate is 234 microliter blank solution in another well, and water in 1 centimeter of a quartz cuvette are these numbers here. Did you guys want to try this out? Yeah? No? Mm-hmm. Yep. Find the path length for the 230 microliter solution and the blank corrected absorbance for the DNA in the 1 centimeter cuvette. And then what is the concentration for the DNA units of micrograms per milliliter if the absorption coefficient is this? Notice this is in micrograms per milliliter already. Try to plug those in and see if you understand where you should plug each number in. It's going to be using that equation we just talked about. Consistent? $0.61? Yep. Perfect. Yeah, it's just plug and play. Yep. Okay. And this is where you get the concentration. You just plug in that adjusted value here, the absorptivity right here, right? And the path length there. And that would give you the micrograms per milliliter. Is that making sense? Okay, let's talk about scattering. Now, the turbidity and nephelometry is going to measure the amount of light that passes through a sample in a forward direction, which is turbidity, or the scatter at an angle, which is nephelometry. This is typically going to be 90 degrees for that scattering at an angle, because that's going to be directly perpendicular to your incident beam. Now, turbidity is going to be suited samples with relatively high concentrations of suspended particles. Nephelometry is actually better for low concentrations of those particles. The sample solution should be colorless. Measurements should be made at non-absorbing wavelengths of those samples, because if you measure them at absorbing wavelengths, you're also measuring absorbance, aren't you? Rather than just scattering. Okay. Applications are going to be things like microbial growth, air pollution monitoring is really good for this. This is actually how most of those, like, have you seen there's like those weather station air pollution monitors? They're like, this has so many particles today. Yeah, that's this. Okay. And so the scattering intensity is getting reported in optical density, which is OD. And this is going to emphasize the turbidity, not the absorbance that is being monitored here. And so this is the absorbance due to scattering, not the absorbance due to actually absorbing at that, because the epsilon, right? Okay. And this right here is going to be your path length divided by 1 centimeter. This is if you want to solve it down, so you can use your light beams as your measurement here instead of absorbance. Okay. Same thing as you used to. Okay. Let's talk a bit about flow injection analysis and sequential injections. Oh, I am out of time. You all have a great day, and we'll pick up from here next time. Oh, very good. Okay. Well, I guess I actually made decent time today, didn't I, for this material? I forgot I actually started at 5, didn't I? Okay. My God, I'm not going to get done with this.